So first of all, just by way of introduction, so this presentation, this part of the session will be presented by Jie Wen. He's a PhD student who's in his final year. He's funded by the ARC. And Jie is going to be talking about the factor-based GLM models. So over to you.
Thanks, Andrew. Hello. Is that clear? Hello. Yeah. Hi. Thanks for coming to my talk, everyone. And as Andrew has introduced, I'm a PhD student studying with Andrew and Thorsten for the actuarial mathematics in the Hillel University. And my topic today is about factor-based GLM model according to a granular level of mortality over the individual LSOAs, as Andrew used to introduce at the beginning. And here is the general structure of my talk today. I will start with a bit overview on what data I use, thanks to Andrew, who has covered most of it already. And I will introduce what does the basic model look like. And then I will talk something about the parameter estimation method and model selection method I used to pick up the best model. And because we have a lot of socio-economic factors available, and I will introduce something about how do we select the most important variables out of the whole wide universe. And last section is about some of the region and urban-rural variation of mortality across the whole England. And then there's summary and Q&A. Yeah, so first of all, the data we use is equivalent to a multi-population data describing England. And for each of the 33,000 LSOAs, we have death count and exposure count available at each time and age. And the total age range is 0 to 90, and the year range is available from 2001 to 2016, but we picked up the pensionable age, which is more of our interest, which is age 65 to 89. And there are a lot of socio-economic related factors available at individual LSOA level. They are related to income, education, housing, something like that. And other than the numerical factors, as Andrew and Thorsten has been introduced, we also have categorical variables describing different features of each individual LSOAs. Before I starting with any of the modeling stuff, here I just want to introduce an alternative mortality measure at LSOA level, which is called actual versus expected death ratio. And so first of all, this calculation is very simple. And first of all, we calculate the total number of deaths at LSOA-I by summing over a specific age and year range, which is DI. And the D hat 0I means the expected deaths at LSOA-I, which is calculated by a common mortality matrix, MBTX times the exposure size, and sum up over a specific year and age range again. And that MBTX is just equivalent to the national level mortality, which is derived by aggregating all of areas together and calculated at each individual year and age. And then the Y here is calculated by DI divided by DI0 hat, which is just actual versus expected. And this mortality measure tells us the story about how does each LSOA have a mortality level relative to the overall national level. And these measures should be centered around 1, and any LSOA having this number close to 1, that means it's close to the overall national level. And any LSOA is having YI significantly larger than 1 or smaller than 1, it means they have big mortality variation from the national level. And the most important advantage of this measure compared to the DITX and EITX is this is a scalar variable at LSOA level. So each LSOA only has one number, which is more convenient for some of the multivariate analysis according to the socio-economic factors. So given that the data we have on hand, here are some considerations of the data. the individual SOEs, as Andrew has been talked about, only have around 1,600 people. So there has limited exposure size and are likely to make the modeling quite volatile. And that's why we are considering to combine the death and exposure data together to calculate the national level mortality at first. And then for the RSOE level granular mortalities, we model them via a top-down approach, starting from the national level and up until the RSOE level. And those socioeconomic factors at RSOE level, which are the variables about income, employment, etc., they are used as predictors to model the RSOE specific mortality. And this method helps us to limit the volatilities from small death and exposure size of each small area. And here is just an example of some of the socioeconomic factors we used in our analysis. And Andrew and Torsten has covered most of them. And we can see there are some of the index under the IMD project. And there are also some of other numerical measures like average number of bedrooms, ratio of equivalent population, something like that. Here is just some of the short names of this index to make the slides less wordy. And before we popping these indices or variables into the model, because most of them, they're constructed by different methods and they are measured by different units. And we have to standardize them first in order to avoid of distorting the modeling result too much. The standardization we follow is the uniform normal transformation. So first of all, based on for all of the original factors F, and for each RSOE I, we rank the scores first, and then we divide it by the total number of RSOEs plus 1, which makes the factor to be a uniform distributed variable. And then next stage, we transfer the uniform variable back to a normal 0, 1 by popping it into an inverse function of normal probability function. And then the xi's here, they are all normally distributed, and they are all following broadly the similar scale of each other. So next, let's look at what does the model look like. It's just as I mentioned before, it follows a top-down approach, starting from national level to the RSOE level. So we start from the MITX as the death rate at RSOE I, which is calculated by DITX divided by EITX. And the MBTX is the overall national level death rate, which is the same over all RSOEs. And the RRITX here means the relative risk factor of RSOE I. So that is this relative risk factor. It describes how does the RSOE level mortality varies over the national level. And the overall model structure is like this. So the log of MITX is equal to the national level mortality plus a shifting factor. So let's concentrate on national part first. The MBTX, it can be measured by different methods. So for example, we can just use the crude national death rates as the measure to calculate the MBTX, or we can use some of the non-parametric modeling structure, and which is introduced by Torsten already. So this is the CBD structure. It takes into account the time varying factor over time, and both of the kappas here, they are common over all RSOEs. So that describes the overall national level. The relative risk factors are RITX. So in our analysis here, they are evaluated as a linear combination of different socioeconomic factors, which is like a GLM predictor. So here, as one of the first example, that's the simple model structure. How does it look like? So we use CBD structure to model the national level mortality, and then we use a combination of different linear predictors as a GLM term to model the LSOE level mortality, which shift up and down from the national level. And as kappas are the period factor that captures the overall national level period pattern over time. And the betas here, they are coefficients of socio-economic factors. And they just map their effects onto, they just measures how big are the effects of each socio-economic factor onto the mortality. And so if we look at this formula, there are two most important disadvantages of this model. First of all, at LSOE level part, there is no age factor at all. It's not related to age. So this structure assumes all of the LSOEs follows exactly the same age pattern as the national level does. And then secondly, if we see the betas, the coefficients, they measures the importance of, or they measures the magnitude of the effect of socio-economic factors onto mortality, but they are constant and then does not vary over time. And that's why this model assumes the factors have constant effect onto mortality over time, which is don't change over time. And these two disadvantage makes this model less realistic. And then that's why we have proposed an extended version of this model. The national level stays the same as the CBD structure, but if we concentrate on the LSOE level, we see for each variable, now we have two coefficients. First is the intercept, which is the baseline. Second is the age interaction term, which is related to age. So by this age interaction, we managed to add age pattern onto the LSOE level modeling as well. And the next thing is for the betas here, we add a T here. So we enable them to vary over time, which can be considered as a time series. Oh, and by the way, the estimated betas here, they can indicate for how much does the corresponding factors contribute into the inequality of mortality over different LSOEs at each individual year. So we are able to see the pattern over time. And this is so as Torsten has introduced already, so this is just follows our parameter estimation approach just follows the quite commonly used Poisson assumption and using MLE, maximum likelihood estimation approach, to model all of the coefficients here. And we assume the death follows a Poisson distribution with the Poisson parameter calculated by the exposures times the m hat, which m hat here can be represented by the model and in terms of the coefficients to be estimated. And then we can build up the Poisson log likelihood. And that Poisson log likelihood, the di hat term, that include the unknown parameters. We estimate the parameters by maximizing the L here. So next section is about the parameter estimation result and model selection method we use to pick up the best model. Same as what Torsten has been presented, these models are selected based on BIC as well, and which is defined by the k times log n minus 2 times maximized log likelihood. K is the number of unknown parameters, and n is the sample size. So this criteria, it penalizes any over-parameterization term. So if a model has too many parameters, it will be penalized by the k term. And following this definition of BIC, the models with small BICs are considered to be better model than others. And one of the first things we try out is to, because we have a whole universe of socio-economic variables, there are a lot of them. One of the first method we use is we just fit this model over different combinations of socio-economic factors. And then we pick up those combinations that gives the most outstanding BIC. There is also some of the expert judgment applied. For example, which predictor to start with and which two predictors, they might work better when they applied all together or something like that. But the first thing we have done, there's not too many intelligence included. Just try out different combinations. And here are the 4 scenarios. They are the 4 combinations that gives the most outstanding BICs. We can see these are the combination of socio-economic factors. We have the income old score. We have employment deprivation score. We have proportion of population have no qualification degree above age 65. We have number of bedrooms, and we have wider barrier score. We have ratio of UK-born population here. And out of these 4 scenarios, the third one, the income owed, proportion of population without qualification above 65, number of bedrooms, and wider barrier score, it gives the most outstanding BIC. So for today, we concentrate on this scenario and dig out more details. And the model based on these 4 variables is something like that. From x1 to x4, they are the 4 listed variables. So first of all, let's look at the estimated kappas. How does the national level kappas look like? There's no surprising at all. With kappa 1, which is a baseline of period factor of national level mortality, and it decreases over time, which shows the mortality improvement over the most recent years. And here's a bit slowdown in 2011. And for the kappa 2, which is the age-related factor, and it's increasing over time. And the increase in kappa 2, and it's positive, it means there has been bigger improvement at relatively young ages. That is, those ages below the average age over the whole underlying age fitted model. And after the national level kappas, here might be more of interest. So here are the coefficients of RSOE level mortality term. So the left-hand side is the intercept, which is the beta O, and right-hand side is the age interaction term, the one produced with the x minus x bar together. And first, so I have plotted the beta intercept and age interaction for all of the 4 predictors here. And if we see the income old score first, we can see the intercept. Of course, it's a very clear increasing pattern over time. The interpretation of the increasing pattern is the income-related factors. They have been contributed more and more into the inequality of mortality over different areas over the underlying year range, 2001 to 2016. And the same thing we can see from the second predictor, the proportion of no qualification population above age 65. There's a clear increasing pattern as well. And meanwhile, for the 2 age interaction terms, they are quite volatile, and there's no such clear pattern compared to the 2 intercept here. And let's look at the next 2 predictors. The average number of bedrooms and IMD wider barrier score. And we see for these 2, both of them, they have neither a clear pattern for the for the intercept or the age interaction. And we can see the average number of bedrooms has a negative scale, which is correspond to our common sense, because the bigger house means means higher income or better living environment, which should have lower mortality. And the IMD weather barrier score here, which has negative as well, which is a bit counterintuitive. I will explain it later on. So here is just a flashback of what does the fraud predictor means. So here are some summary about what have we found out of the estimated parameters. So beta 1.0 and beta 2.0, they are increasing over time, which means they are increasing contribution to the inequality of mortality from that two factors. And meanwhile, beta 3.0 and beta 4.0, they have no clear pattern, and their fluctuations over time are more likely to form sampling variation instead of genuine pattern. And the RSOEs with larger value of income old score and proportion of no qualification people, they tend to have higher mortality, of course. And the weather barriers here has negative sign, which is a bit different from our expectation, because there are some more than one reason driven this result, and some of them, one of them is about effects of London-based RSOEs, because the RSOEs in London, they're quite special. First of all, they tend to have more deprivation in general. Secondly, they tend to have much higher income compared to others. And for the weather barrier score, because of it's related to housing affordability and housing overcrowding, something like that, and which act as a kind of interacting factor of other facts of the London-based RSOEs. And also, from the modeling perspective, because of the different predictors, they are relative to each other. They are correlated to each other. So they might be interacted with each other. So, for example, the income old score is the dominating variable. That's why, and then the income old score might absorb those effects out of the weather barriers, and then the weather barrier is only left with some residual effect. Here are some further considerations according to the behavior of the estimated coefficients. So first of all, except for the beta 1.0 and beta 2.0, all of other coefficients, they don't have any significant pattern over time. They just fluctuate. And that's why we think their fluctuations over time are more likely to form sampling noise instead of a crude mortality pattern to capture. And then we expect they can be simplified to constant instead of time varying pattern to save a bit more parameter space. And actually, after we made such simplification, we see from the original model, we only keep the time dependency for these two, and then we remove time dependency for all of others and turn them to constant. The BIC has improved further from this to this for around 1,300, which is quite a big improvement because there are much less coefficients to be estimated. So the model becomes simpler without losing too much information about mortality. And this model is still some of the under our working process, and we might dig out more information, and we might make further adjustment onto this format according to make it more reasonable, more simple, and capture more meaningful effects from the crude data. So after we estimate the parameters, after we try out different combinations of variables, we have found out that over the universe, over the data set, we have too many variables that could be potentially important to model mortality. But we can't use all of them, otherwise there's a significant overfitting problem and computational burden. And that's why, as a part of the GLM modeling we also work on the variable selection by different techniques in order to pick up those most important variables while dropping out those less important variables. And the first variable selection method I'm talking today is the shrinkage method. And Lassell is one of the most commonly used shrinkage method, which is automated variable selection, which doesn't require too much expert judgment. And the full name of Lassell is like least absolute shrinkage selection and operator. And so, but more important here is to introduce how does it work. Lassell works in a very easy way. So it also estimates the coefficients following some objective function. For example, here we use MLE, so the log likelihood function, the Poisson log likelihood function is our objective function here. So Lassell, instead of maximizing the full log likelihood function, Lassell maximizes the penalized log likelihood function with additional penalty term, which is a lambda, a penalty factor, times sum of absolute value of all of the coefficients to estimate. Because of this penalty, if we maximize the whole thing instead of the full log likelihood, those parameters estimated will be squeezed down to a lower size, will be squeezed down to 0. And some of them, they might be squeezed down to 0 exactly, to be equal to 0. And some others might be squeezed down to a lower size, closer to 0, but not 0. So everything is controlled by the lambda here. So if lambda is 0, then it is equivalent to a full MLE approach. If we increase lambda from 0 to a larger value, the coefficients will be squeezed down to a lower size. And we can measure the degree of shrinking by the metric called shrink ratio of Lassell, which can be written as a function of lambda, which is a fraction, so a ratio between those sum of absolute value of the shrinked betas divided by sum of absolute values of the betas from the full MLE approach. If lambda is equal to 0, then shrink ratio is equal to 1. Once lambda increases from 0 to a larger size, the shrink ratio is going to be smaller than 1. If lambda is big enough, shrink ratio is closing to 0. And as I said here, as lambda increasing from 0, the estimated coefficients beta hat, they are shrinked and reduced towards 0. The point here is, if we fit this model, if we fit this method to multiple parameters, multiple variables, some variable will have their coefficients shrinked down to 0 later than others as we increasing the lambda. Then those predictors with coefficients shrink down to 0 latest is suggested to be the most important variables. Sorry. And here is a bit of information it's worth to mention. Because of our purpose here is to pick up the most important variables instead of modeling the mortality accurately. So we use a simplified version of the GLM model. And we see we have taken out the time dependency, and we have removed the age interaction as well. And because of there's no age interaction here, and this model is more meaningful to fit over relatively narrow age ranges. For example, only 5-year or 10-year age groups, because it doesn't capture an age pattern at RSO level anymore. So let's see some results here. So first of all, if we concentrate on age 41 to 45, the x-axis is the shrink ratio, and the y-axis is the estimated coefficients of these different variables. If we start from the right-hand side here, when shrink ratio is equal to 1, lambda is equal to 0, so it's equivalent to a full MLE estimation, and we have these coefficients. As we increase lambda from right to the left, and we can see all of them, they start to be squeezed towards 0, and some of them, they are reduced to 0 later than others. And those variables with coefficients reduced to 0 at the slowest speed are suggested to be the most important one. And we see for this age group, we see the employment is the IMD employment deprivation score is the most outstanding one. And then we also have, from another side of x-axis, we have number of bedrooms. And then if we jump back to the positive side, we have income old score here as well. And these three variables are most outstanding over this age group, 40 to 45. And then if we look at age 61 to 65, we see similar pattern, but we see different outstanding variables. We see proportion of population without qualification above age 65. We see income old score. We see wider barriers. We see employment score. And then if we have a look at age 81 to 85, and we see the same four variables has been highlighted here. So as a summary, according to Lassalle, we have these variables suggested to be important over these three distinct age buckets. And the variables here are broadly consistent with those giving the best BIC in the GLM, which is good news to us because it supports our result extracted from GLM fitting. And the next variable selection technique I'm talking here is about regression trees and random forest, which is a bit more modern technique, more flexible and more fast. So they are not designed for variable selection specifically, but variable selection can be also taken by this method. They are tree-based method. They are supervised learning techniques, and they are non-parametric, which means there's no closed form formula. They have functions, but you can't write them into something like what fx equal to ax plus b. No. And here in this talk, they can be alternative to BIC or Lassalle for selecting the most important variables out. And the way they work is they split the training so before getting into forest, we have to start with trees because forest is made up by individual trees. So the regression trees, they split the data set, which are the LSOEs, by values of input variables, which are just the socio-economic factors, into different groups. And each split is made by only one variable. And the input response variable y, we use the actual versus expected ratio here. And we use the AE ratio can be picked up over a certain age range to represent mortality level of individual SOEs. And all in all, the tree method, they are equivalent to nonlinear regression. So we can consider them as a nonlinear regression. Y hat equals to a function of the input variables, but there's no closed formal formula for this F. And over each regression tree, each split driven by a specific variable is called a node, and the two distinct groups under each node is called leaves. And the final groups splitted are called terminal nodes. And within each final group, so each final group will have a selection of observations, which are LSOAs. So within each final group, the estimated y hat is calculated as the average of over all of observations classified into that group, which is quite simple. And the question here is when to split and what factor do we use to split. These are driven by a principle here. So the variables to split at each node is selected such that the overall mean squared error is reduced for the most extent. And then there are some specific stopping criteria when we can stop splitting the trees. The explanations here might be too abstract, so we can show some visible example here. So it's a very easy example of a single regression tree with only two variables, income owed and employment. We make a regression from these two variables towards the y, which is the actual versus expected ratio over age 60 to 69 as an example. So in order to find the best split, we search over the two dimensions one by one. And here we have identified if we split the income owed score by 0.351 and all of the RSOEs in this region, they have the same y hat, which is the average of all of them. And all of other RSOEs in this region, they have exactly the same y hat, which is the average of all of these RSOEs. And we have picked up this point because this point gives us the most significant reduction in the MSE. And then next, following each of these areas, we find next splitting point. Here. And we have split further by the income owed score. And we have 4 nodes here. We have 4 groups here. And all of the RSOEs in each of the 4 groups have exactly the same y hat, which calculated as the average of all RSOEs in the same group. And then we start to search again to look for some further split. And we have found the split according to another predictor, which is employment. And here are 2 further splits. And then up to now, we have hit the stopping criteria. And then the algorithm stops. For each of the distinct areas, the RSOEs in a specific area will have exactly same y hat, which is the average over all of the RSOEs in that area. And for summarizing the tree, so this is just the overall structure of the tree, what I just shown you. So we start from the first split, the income owed score, and then we split all of the RSOEs into 2 parts, and then we split it further, and here we split it further by the employment score. And we have 6 terminal groups, and with each group have a y hat to be same over all RSOEs in that group. So this is how does one single regression tree work, which is non-primary tree because there's no formula you can write. And then it's very easy to understand. Forest made up by a lot of trees altogether. And random forest grows a set of trees. But the most important thing is that each tree, they are growing from a randomly selected subset of observations and a randomly selected subset of variables. That means all of the trees, they are different. They are based on different observations, and they are based on different variables, which means they are not highly correlated, which reduces the overfitting risk to a great extent. And the output of the random forest is just an average of the output of each individual tree. We average over the whole forest. And to be honest, the random forest is designed for prediction purpose. So it can be used for regression if y is numerical. It can be used for classification if y is categorical. But here we use random forest to investigate the variable importance. And there are some other tree-based methods which also could be very helpful to select the variables. For example, gradient boosting machine, but I won't introduce to any details today. Here is just an example of how does random forest work. For example, here is the data we have, right? We have RSOAs, and we have the variables x1, x2, to xp. And for the first tree, we pick up the red observations. We pick up the first RSOA, we pick up the second RSOA, and we pick up the fourth, fifth, seventh, etc. And for the variables, we pick up the first variable, we don't pick up the second one, we pick up the third, we pick up the fourth, and we skip over all of these, and we pick up the fifth. All of these selections are done randomly for each individual tree. And those red ones, they are selected RSOAs, and they are used to grow the tree. For the other unselected observations, they are called out-of-bag samples. They are left aside for each tree, so they are not used at all to grow the tree. Sorry. And following the way, how does the random selection work? The random forest can provide us two different measures of variable importance. First is the percentage increase in the MSE. So that measures the increase of out-of-bag MSE after a specific variable is randomly shuffled. And it is measured as a percentage of original out-of-bag MSE. And we calculate this metric for each individual tree, and we average over the whole forest. It might be abstract, but if we look back into this graph, so first of all, for example, for the first tree, we pick up the red ones, and we grow the tree, we have the tree, and we use the tree to predict those unused observations. And then we can calculate the out-of-sample MSE over the black ones, the unused observations, which is the first MSE. And then if we want to investigate the importance of first variable, for this x1, we randomly shuffle the x1. So we just make it messy, and we just randomly reorder the whole vector. And then we calculate the out-of-sample MSE again over those unused samples. In principle, or under most of the cases, the new MSE should be higher than the old MSE because one of the variables has been destroyed. And that increase of MSE is just the first measure of importance. And the second importance is a bit easier to understand. It's the total reduction of in-sample residual sum of squares from all split in a tree that is driven by a specific variable, and it is average over all trees. And we can look back to the whole structure. If we want to calculate the importance of income old score along this tree, and we can, so here's one split, two splits, three splits. There are three splits according to income old score here. And following each split, the residual sum of squares is reduced for a little bit. And then we just sum up the reduction in the residual of squares over these 3 points. And we average over all trees, which is the second tree, which is the second measure of importance. And all in all, broadly speaking, these two measures, the measures how does each variable affect performance of that model. So the importance of a specific variable is quantified as how does it improve the model performance out of sample or in sample. If a variable is able to improve the model performance a lot, then it is higher chance that that variable is more important. And I will show some results here. And here is the random forest constructed by the A versus E ratio over age 60 to 69 as the Y variable over the set of 27 X variables in total. And the first table is the top 10 variables giving the first measure. And second table is top 10 variables giving the second measure. And we see for the first table, and we see the proportion of population living in care home with nurturing is the most outstanding one. And we also have a ratio of UK-born population. We have proportion of no qualification population. We have number of bedrooms, income owed. And for the second measure, we have income owed, employment, and proportion of no qualification, number of bedrooms, education, something like that. And these variables highlighted are broadly consistent with what we found by the previous two approaches. And so the next section today, I will speak quickly regarding to the regional and urban-rural pattern of RSOEs. So as Andrew has mentioned, all of the RSOEs, they are divided into 9 regions and 5 urban-rural classes according to level of urbanization. And here are the 9 regions. And here is the distribution of the RSOEs in the 9 different regions. And here are the 5 classes of urban-rural classes. And we have taken out London from class 1 and built up class 5. And here is the distribution of the urban-rural classes. And we see that there are clusters of class 1, which means big cities like Birmingham, Manchester, Newcastle. And we have the London as the class 5 at the south part. And because we believe there's a variation of mortality across RSOEs in different regions. And if we fit the model over all RSOEs without allowance for any regional or urban-rural variation, we might lose some of the granularity of information. That's why we have tested the model. This is exactly the same model as what I have talked with the same structure with time dependency with age interaction, but the only difference is this model is fitted to RSOEs in different regions or urban-rural classes separately in order to highlight the difference across these groups. So RI here is the corresponding region or UR class that RSOE I belong to. And so here is the estimated kappas at national level, and not at national level, it's regional level or class level. So kappa 1, kappa 2, and we see from kappa 1, of course, there's a mortality improvement over time for all of the urban-rural classes, but there are very clear ranking from high to low mortality over across different classes. And we see, if we ignore London first, and we see those more urbanized areas tends to have higher level of kappa. And London has the lowest kappa. And London also has the most significant improvement over the most recent years, while the class 1 and class 2, they have a outstanding kink here. And this 2011 slowdown is more associated with those more urbanized areas, except London. And so for the kappa 2, for the age interaction term, we see there's increasing, of course, which is same as the common trend. And we see that the urban-rural class 4, the villages, the smallest, like the rural villages, they are most age sensitive. And, sorry, I forgot to mention that. So this model, for now, is fitted over the income owed score only. So it's a univariate model. And here is the estimated beta 10 and beta 11 associated to the income owed score. And we see for the beta 10, of course, they are increasing over time, which means the income-related factor are contributing into the inequality over RSOEs more and more over the most recent years. But we see London and the urban-rural class 4, the least urbanized areas, they have the lower inequality contributed by income factor compared to other classes. And meanwhile, for the age interaction term, this is quite volatile and not too much information we can extract from out of it. And so as a initial conclusion of the region and urban-rural analysis, we see the London-based RSOEs, they have significantly different behavior from most of others. And the slowdown of mortality improvement at 2011 is more related to RSOEs in class 1 to 3 rather than 4 and London. And the class 4 RSOEs is more sensitive to age. And we also fit the model to separate regions as well. So there are 9 regions in total, but which I didn't include that into the slides here. And the regions and the results shows those regions with higher mortality level, they have least improvement over time. So as Thorsten has been mentioned, those high mortality areas, their slowdown is much more significant. And the northwest and northeast are the 2 regions with highest mortality compared to most of others regions in England. So as a summary today, and according to the variable importance and variable selection analysis, we have figured out income, employment, education, and housing-related factors. They have the relatively strong predictive power to mortality. And income is one of the most important variables, and it is also the main contributor into the increasing inequality over different areas over time. And there is significant heterogeneity of mortality over different regions and urban-rural classes over the most recent years. And lastly, London-based RSOEs, they have quite different behavior compared to others. And just a brief summary of some of my future researches. So I will do some work on the selective age interaction and time dependency of the GLM model, because some of the variables might not need time dependency, as I have outlined. And based on the current findings, I'm trying to finalize the GLM model and trying to figure out the most appropriate structure that could capture as much as mortality information while without using too many coefficients, which gives the best BIC. Yeah, that's the end of my speak. Thank you very much for listening today.
So I think we've maybe got time for one question, and then we need to move on. So over here. And there is more time at the end of the whole session, but it's, some people might need to drift away at that point.
Is that on? Can you hear me?
Yeah.
Thank you for that. Could you give us an indication, sort of cutting through all the detail? Because we're obviously, we're all probably in this room quite familiar with the IMD, just basic off-the-shelf IMD. So we've seen that earlier, and we've seen differentials, and we've seen differential trends. How much more do you get from sort of unpicking it and putting it back together in a slightly different weighting, which is broadly what you've done? Do you get a little bit more differentiation, or are we seeing quite a lot more here? And sort of 2 questions really, one with the unpick and then one with the unpick plus rural and urban.
So I think maybe rephrasing that, it would be a case of when you looked at the BIC, for example, and if you compared the model that uses separate variables and estimates their individual betas, if you then compare that with the BIC for, if you just use the IMD only.
So it's a comparison of regional or urban-rural class specific model compared to the model fitted over all RSOEs as in one go. Do you mean this?
I'm kind of trying to get a sense of how much better is this versus the off-the-shelf IMD? Given that a lot of these things are already in there, so I think we saw that income and employment might have been 22.5% each, and so you're kind of building up something that's getting towards the IMD,
right,
especially when all those subfields and subdomains, etc., are all highly correlated. Is this, how much better is this?
I think first of all, to be honest, in respect of comparison between the IMD and this model, I think we haven't got too much comparison between these two models yet. And this model, so I think the most important advantage is to gives you more granular information, and then, as Torsten has mentioned, IMD include the health score as well, and we just deliberately dropped out the health score from this analysis, and that's one of the most important improvement. But in terms of comparison, according to IMD and this one for their BIC, we haven't done too much stuff on that yet.
Thanks. I think that would be a useful thing to add into your work, just to give us a guide as to how much more.
How much of an improvement? Yes. I mean,
that might be the next stage after I finalize the model structure with the most appropriate variables.
I think with the various strands of work that we're doing, we do sort of start off by looking at these very simple measures, such as IMD as a single predictor, but then you very quickly leave that behind when you go into these other variants. I think, well, yes, I mean, the point is good that we need to then just go back and say, well, how much of an improvement is there? And I think it's certainly quite substantial, but you know,